Welcome to RF transceiver design course. We are discussing about the mixer design. We are on module 8, lecture 43. So, what we have done in the last class, we are discussing about the mixer parameters and what basics of the mixer. So, now one of the parameter we have seen is isolation. Now, another important parameter for the mixer is a conversion gain. So, here it is a possible that in the mixer, if you are designing for very high frequency for sub terahertz and all, it might add the loss. So, if for that there is either conversion gain or conversion loss. It is a ratio of the desired IF output voltage or power to the RF input signal value, either voltage or power. If you consider the voltage, RMS voltage and IF by RMS, it is called as a conversion voltage, gain conversion voltage, and it can be a gain conversion power if we consider IF output power by RF input power. And as we have seen that we can consider that if your IF impedance at the load and input are matched, then we can also write down voltage gain equal to power gain. So, now here it is important to understand the meaning of conversion. So, here your RF frequency, let us say if you are at omega RF of 2.4 gigahertz, you have given input power of minus 40 dBm. So, this is our mixer, this is a omega RF input, this is omega LO and this is omega IF. So, at omega RF is equal to 2.4 gigahertz, you have a minus 40 dBm, that is the input power, and your omega IF is 100 megahertz, because if you make omega LO as a 2.3 gigahertz, omega RF is 2.4 gigahertz, then omega IF is 100 megahertz. So, in amplifier what we see is a same 2.4 gigahertz and output also has the same frequency, but here your output has a different frequency, that is 100 megahertz. And as we have seen in the last class, we do not want RF power to be fed through to the IF. We need isolation between RF and IF port as well. So, this is our desired frequency, which is 100 megahertz, and at 100 megahertz if your output power is minus 30 dBm. Then what is your conversion gain? Because here there is a two frequencies are involved, your RF frequency and IF frequency both are different, we are considering the conversion gain, and that is why your conversion gain, it is also denoted by Cg, it is Cg conversion gain, which is equal to, let us say, power at IF divided by power at RF. We can write in dB PIF minus PRF. So, which is equal to PIF is minus 30 minus 40. So, we will get a 10 dB. So, the conversion gain is a 10 dB. If there is a your IF at omega IF, instead of minus 30 dB you have a minus more than less than minus 40, minus 45, then it is also mentioned as a conversion loss CL. So, there might be a conversion gain or conversion loss. So, this is very important parameter for a mixer. Then another important parameter is the input intermodulation product, IIP3. We have already seen IIP3 for the low noise amplifier or amplifiers, that if there is a omega RF signal, omega RF1 signal, omega RF2 signal, then it has a intermodulation product 2 omega RF1 minus omega RF2 or 2 omega RF2 minus omega RF1. So, there is a 2 intermodulation product, and then we have drawn the first and third order harmonic. Now, when we consider the mixer, what we need to also consider is the down conversion of the intermodulation product also. So, here you have given a 2 tone, that is RF1 and RF2, and there is a LO, that is the input. So, when you are, because this is your mixer, you have given a RF signal, means 2 RF tone, RF1 and RF2. This is RF1 and this is RF2. So, what will happen, that you will have a at output 2 omega I, means omega IF1 and omega IF2. So, this is omega IF1, this is omega IF2. So, omega IF1 is RF1 minus it is RF1 minus LO, and this is RF2 minus LO. This is not a amplitude, this is a frequency, RF1 minus LO and RF2 minus LO. And the third order component, that is the 2 omega RF1 minus RF2 minus LO. So, when we consider the mixer, we need to subtract the LO in the third order component. So, this is the third order LO. All others derivation is same, only when you are considering the mixer, you need to subtract the LO. If it is the upper side and lower side, you need to consider the omega IF1 and omega IF2. You can also write it down, this is omega IF1, this is omega IF2. Then your third order component will be 2 omega RF1 minus RF2 minus LO, and this is 2 omega RF2 minus RF1 minus LO. So, this is how we can have a IIP3 for the mixer. So, you can plot the third order harmonic and the first order harmonic. So, this is the third order component and this is a first order component. You can plot the third order and first order. The point at which third order and first order intersect is, that point is called IP3, that is the intercept point 3. Why it is a 3? Because it is a third order, that is why 3. If you consider a second order, then it will be IP2. So, here it is a 3, so that is why IP3, and then there is a IIP3, that is if it is at input side, it is called IIP3, and output side it is a OIP3. So, input intercept point and output intercept point. So, here your IIP3 is P in plus delta by 2. So, what is the delta? The delta is this difference, and remember that P in here. So, this P in is a RF frequency input power. So, this is a RF frequency input power, and delta is the difference between the first order at IF and the third order at IF, and this is a IIP3, and delta difference we already have discussed, and here the OIP3 is the IIP3 plus conversion gain. Instead of gain, it is a conversion gain in dB. So, OIP3 has a relation with the gain and IIP3. So, only difference here, that when you consider the second order, means when you consider the mixer, you should subtract the LO frequency, and you should see the at omega IF, you should see the IP3 at the intermodulation frequency. So, if we summarize that, what are the different metrics, mixer metrics. So, this is these are the mixer metrics. Then one of the mixer metrics is the conversion gain. So, it is obvious that if you have a better gain, then it lowers the noise impact of the following stages. We already know the Price formula, f1 plus f2 minus 1 by g1 plus f3 minus 1 by g1 plus c2. So, if it has a gain, then again it will reduce the noise of the entire system. Noise figure, it impacts the receiver sensitivity. Port isolation, it is to minimize the feed through between the RF, IF and LO port. So, we need to minimize the feed through. Linearity, it impacts the receiver blocking performance. We already have seen that that desensitization and the intermodulation, how it will means if there is a not better linearity, there is a possibility that it cannot block the other blockers. So, that is why linearity is also important. Power match, we want a maximum voltage gain rather than power gain, because when we are using a and when we are designing an entire RFIC on a single chip, we consider the voltage gain, because we are not doing the impedance matching at each stage. Our first stage is driving the second stage, which is a capacitive load. So, that is why we are considering the voltage gain. If let us say if you are making a discrete, using a discrete component and then making a receiver, for that case you need to do the power match also, otherwise your receiver might have a more reflection and it will not work. But on chip you can consider it as a capacitive load. Then there is a power, obviously you need to design your mixer which has a lower power dissipation, and you can also use a configuration which do not consume so much power, and there is a sensitivity to the process or temperature variation. So, need to make it a manufactures in high volume. So, these are the various parameters that mixer metrics we can say that we should consider while designing the mixer. We will try to see the different kind of topology for the mixer design. So, before going to the individual topology, we will see that how the evolution of mixer happens. So, from the tube based diode ring to the FET based linear mixer. So, initially there is a diode based mixers were widely used. It is not absolute, because now we are at the age of now we are going in the 6th generation technology. We are going to use the sub terahertz, and in sub terahertz if we have a Schottky diode which is a higher FT, then we can also use that diodes to make a mixer, and that can down convert very high frequency to the lower frequency, and it can also be integrated in the waveguides. So, the whatever mixer design that we will discuss, that can all the design has its own application. So, diode ring mixer structure, it employs the Schottky diode. So, Schottky diode is fast in switching, and it can also switch up to terahertz. Schottky diodes are available, and input and output signals connect to transform link to the ring, while a differential LO signal is applied to the center tap of the transformers. So, this is how diode ring mixer works. How the switching operation, during one half cycle of the LO signal, specific diode are on while other are off. this results in a output being equal to the input, and during the next half cycle the polarity of the input and output reverses and leading to the output multiplication by a function of a Pt. So, Pt we already have seen in the while discussing the FET based switching mixer, that is a 4 by pi sin omega L O t minus 1 by 3 sin 3 omega L O t plus 1 by 5 sin phi omega L O t. So, here LO amplitude requirement to ensure a proper diode switching, the LO signal minimum required amplitude to on the diode. So, that is a to turn on the diode, and your mixer output is 2 by pi a cos omega R f minus omega L O t. If you consider the down conversion, if you consider the up conversion, it is a omega R f plus omega L O t, and your LO signal need not to be a square wave, it is not always, it can be a smoothly transition signal provided it to switch the diode effectively. So, if it is done, then you can use it as a LO signal, and it is in the most case instead of square wave, because at high frequency square wave morely go towards the sine wave. That is why we can consider it as a sine wave also. Now, the transition to the FET based mixer in 1968, the researchers from MIT proposed using FETs as a switch and making a transition from diode based mixer. So, diode has been replaced with the FETs, and FETs provide a better switching capability, and it is a result in a more linear mixer. So, this is how the FET based mixer can be evolved. So, initially there was a diode based mixer, and then there is a FET based mixer. So, this is a single ended diode based mixer. So, a diplexer is used to combine RF input and LO input. This is a DC block to block the DC. This diode is in the region where we can consider it as a square law device. So, this is a VRFT which is given by VRF cos omega RFT, VLOT which is VLO cos omega LOT. Now, if we consider the small signal diode current, we need to bias the diode, and then if we consider the small signal diode current, it is given by I naught GD VRF plus VLOT plus GD dash by 2 VRFT plus VLOT square. If VRF is given by cos this signal and VLO is this signal, if we add this, we will get a IIFT, which is a combination of VRFT, VLOT. So, if we multiply here, if we consider the square, then our IT, which is equal to GD1 by 2 VRF cos omega RF t plus VLO cos omega LOT square. This will be squared, this will be squared. We are interested for the combination of these two. So, what you will get is a cos omega RFT into cos omega LOT is multiplied with VRF and VLOT. So, this is a VRFT VLOT, and you will get a cos omega IFT. So, this is the output IF, and that is a filtered out. So, other frequency component which are generated are filtered out by using this filter. Then another single ended FET mixer. So, in that diode has been replaced with the FET. So, there is a RF and LO input is combined by using a diplexer, and it is matched. There is a RF choke is used to bias the FET, and then this is at the gate side, this is at the drain side, and then LO is bypass. You can bypass the LO because there is very high feed through. Your LO signal has a higher amplitude and there is a low pass filter. If we try to do the small signal model, if you try to make a small signal model, this is represented as a VRF input with a impedance of ZG. This is a VLO input with the impedance of Z0, and then there is a RI, that is the input impedance at the when we see at the MOSFET side. This is a CGS capacitor. If we neglect the CGD, and then the current in the FET is GM into VC. This is a load RD, and then you will have a ZL IF. Now we will try to find the conversion gain of the same. So the first equation, what we want is a PIF available by PRF available. So if we consider the current I, so this is the I square into RL, and this current I is due to the at IF frequency VDIF square by ZL square. So because we are considering at the load side, and we are seeing the down converted signal RL by ZL square, and this is PRF that is available, that is a VRF square by 4 into RG. So this will be multiply, this will go up 4 RG by RL by ZL square, and then VDIF square by VRF square. Now what we are interested that how this VDIF is generated from the VRF signal. So we need to use a MOSFET equation in small signal, that is a GMT into VC RF T. So G naught is multiply VC RF cos omega RF T plus 2G1, it is a VC RF cos omega RF T and cos omega LO T is multiplied. So and then it will go on. We are interested to consider the cos omega RF because this is high frequency which will be filtered out. So what we are interested that at GMT VC RFT, if you consider the omega IF at omega RF, G1 VC RF into cos omega FT, which is cos omega RFT minus cos omega RF minus cos omega LO T by 2. So it is G1 omega C RF into cos omega IF T. Now what is the VDIF? So your VDIF is G1 into C RF VC RF and then RD ZL by RD plus ZL, because there is a 2 resistance. So we are considering the output across the both. So the total resistance is a combination of this parallel resistor and your VCRF, because your VCRF is a given at the capacitor. So it is forming the RC low pass behavior like this. So this is a CGS and this is a RI. So that is why we are writing G1 VRF by 1 plus J omega RF CGS RI plus ZG into RD ZL by RD plus ZL. Finally, GC, if it is not matched, if you do not consider the matched, we can write it down a 2 G1 RD by omega RF CGS square whole square, then RG upon RI plus RG square plus. So here it is a mode XG minus 1 by omega RF CGS square RL by RD plus RL square plus XL square. So here what is considered that ZG is divided into the two part RG plus j xg and ZL is RL plus j XL. So, here there is a, if the same thing is considered in this equation, and if you take the magnitude out of it, this is the equation. Now, in this case, if you consider Rg is equal to Ri for matching condition, if you consider Rg is equal to Ri, so the final equation of the conversion gain came while considering Rg is equal to Ri, Xg is equal to 1 by omega Rf into Cgs, and Rd is equal to Rl, and XL is equal to 0. If you try to, this is a not match and this is a match, if you match all your RF LO port with the FET impedance at the input side as well as at output side, this is the final conversion gain, which is a depend upon the first order GM, then RD, frequency omega RF, CGS into RI square. So, this is the conversion gain that we will see at the output. So, we will try to see the example that how this can be calculated. So, a single ended FET mixer is to be designed for a wireless local area network receiver operating at 2.4 gigahertz. The parameter of FETs are RD is the 300 ohm. So, this is a parameters that you are getting after biasing your circuit. So, your RD is equal to 300 ohm, your RI is a 10 ohm, your CGS is 0.3 picofarad, your G1 is a 10 millisiemens, and calculate the maximum possible conversion gain. So, this is a straightforward application of formula. What you need is you need to use the same formula G1 square RD by 4 into omega Rf square Cg square into Ri, you will get around 15.6 dB of a conversion gain. But what is the condition? That your input side, all the condition of the matched should be satisfied, then only you will get the maximum gain. So, this is the FET mixer. We have also seen the diode mixer. So, note this value does not include losses due to the necessary impedance matching network. So, if you add the losses of impedance matching network, then we need to reduce your conversion gain will reduce compared to the what you are achieved. So, this is how the design of the FET mixer, it was widely used before there is a RFIC, means because it is made by using a discrete components, but you can this is nowadays it can also be applicable if you are going for very high frequency, where we want to make a components only a single mixer component to do the down conversion, there also it can be used. We will discuss about the more architecture in the upcoming classes. Thank you.